Okay, so let's look at the first question of this passage. It says, based on the passage, which type of inhibitor will provide a flavorful onion that does not cause tearing? An inhibitor of blank. So we have to go back to this passage. This is purely a passage-based question. We have to see what it is, what component it is that causes tearing. So let's look at the passage, and we see that compound 4 is the potent lacrimator or the tearing agent. So we have to somehow block compound 4. So what makes compound 4? We know that compound 4 is made by LFS. It's the enzyme that makes compound 2 into compound 4. So what we have to do is then block LFS. So inhibiting LFS would be the best way to inhibit or to prevent the tearing. The rest of these answer choices, they're not related to the compound that makes us tear up, I guess, and that's compound 4. Again, LFS creates compound 4, get rid of LFS, no more compound 4, no more tearing. Okay, so this is the next question. It says, when the covalent attachment to alanase, alanase is broken, PLP is still held rigidly in the active site by a salt bridge and a pi stacking interaction. These interactions are most likely provided by the side chains of which amino acids? So what are salt bridges? Salt bridges, these are, oh, there we go, electrostatic reactions, so like a positive charge and a negative charge. These, they attract each other, and that's going to cause that attraction that holds PLP in place. What are pi stacking interactions? This is a little bit more complicated, so I won't go too much into it, but it's basically when you have molecules with pi bonds in them, and they kind of like stack on top of each other. So if you want to think of like these, well, this is terribly drawn, but if you want to think of like two benzene rings on top of each other, these pi bonds, they have these p orbitals, and they essentially interact with each other such that they kind of hold these two benzene rings together. That's the basics of pi stacking interactions. What you need to know is that pi stacking interactions require you to have double bonds. Okay, especially aromatic rings. There we go. I believe, I'm going to double check that, but you do need aromatic rings for pi stacking interactions. So where do we get double bonds? Where do we get aromatic rings? Note that the salt bridging amino acid is listed first, so that means the second one is going to be the one that's responsible for pi stacking interactions. And the only one that we know have aromatic rings are tyrosine, so we can immediately rule out B and D. Now, we're stuck between aspartate and arginine. Remember, aspartate, that's going to be a negative charge at the pH that we're probably thinking about, which is around 7 in the body, and arginine is going to be a positive charge in that environmental pH as well. So again, aspartate, that negative charge, arginine is going to be a positive charge. And how do we differentiate? How do we know which one is going to be which? All right, so we have this PLP molecule in this protein, all right? We know we have the pi stacking interactions, all right? So let's say we have the pi stacking interactions here. And then somehow we have some kind of electrostatic salt bridge forming over here. Now we have to think of this PLP negative charge, or positively charged. If we know that PLP is positively charged, we know this amino acid on the protein is going to be negatively charged. And if you know that PLP is positively charged, then we know that the amino acid over here is going to be negatively charged, and vice versa. So then what charge is PLP? Now, we go back to the passage, we see that PLP is made out of a 6-membered ring, a hydroxyl group, an aldehyde group, and a phosphate, okay? What is a phosphate? Phosphate is going to look like this. Some variation of this, but it does usually have one of the oxygens is deprotonated at the pKa, or the pH that we usually work with, which is around 7. So this means that at least one of these is negatively charged, meaning what? PLP is also going to be negatively charged. So in order for a salt bridge to form, if this PLP molecule is negatively charged, then the amino acid that's forming the salt bridge, it's going to have to be positively charged, right? Opposites attract. So which one of these is positively charged? It's going to be the arginine, making C the correct answer. All right, let's take a look at this next question here. It says, which reactant and product, one equivalent each, are necessary to balance reaction 1? So let's take a look at reaction 1. All right, so this is reaction 1. What do we have here? We have 3 oxygens on this side, but we have 4 oxygens on this side. Okay, so that means the reactant is going to need 1 more oxygen here. And we'll notice that we're missing a source of nitrogen on the product side. So that means we need something with 1 oxygen here, and we need something with a nitrogen on this side. So let's take a look if we can eliminate anything. We can immediately eliminate C and D because we see that, well, C not only adds oxygens into the product side, but it also adds 2 oxygens onto the reactant side, right? So what's happening here in C is you're actually adding an oxygen to the product side ultimately, since you add 2 on the left, 3 on the right. That's equivalent to just adding 1 on the right. And then for D, we're adding just 2 oxygens on the left, the reactant side. And like we said, we only need 1, so we can't be C or D. So between A and B, what do we see? Again, for A, we see that we're adding 3 on the right and 1 on the left for the oxygens. So that's, the same as just essentially adding just 2 oxygens on the right. And like I said again, we need 1 oxygen on the left and 1 nitrogen on the right. So we know that it can't be A. Sorry, that's the next question down there. So that leaves us with B, 1 oxygen on the left and 1 nitrogen on the right. So this is kind of a shortcut way. I didn't really go over any of the other, I guess, elements. I didn't exactly count, for example, the number of hydrogens. But if you do have the time, go ahead and do that. However, notice how just through eliminating the other answer choices, we can immediately whittle the answer down to the correct answer, which is B. But again, do check your answers if you do have the time. This is just a quick and fast way to do this. All right, let's take a look at the next question and the final question of this passage. This says, which energy features characterize the energy profile of reaction 2? Let's take a look at reaction 2. This is reaction 2. And what does the passage say about reaction 2? It's spontaneous and it's rapid, okay? So reaction 2, it is not only spontaneous, it is fast as well. So what does that mean? So what does fast mean? If something is rapid, something is fast, what does that mean? That means the activation energy has to be low, okay? This is just a fact. About kinetics, remember if we're looking at a reaction diagram, this is the activation energy, all right, this difference right here. The lower it is, the faster the reaction, right, because it's easier to get over this hump. So because we know this is a rapid reaction, we know that the energy, activation energy has to be low. Now, what about the fact that it's spontaneous? What does spontaneous mean? It means the delta G is negative. This is just a fact, all right, in thermodynamics. So do memorize that, and from that, we know it can't be C, and the answer has to be D.